This topic is squares modulo prime. Let's start with an experiment. Take prime 11 and compute squares of all residues modulo 11. Well, 0 is always 0, is not interesting, but 1 is also not interesting, but it is good for the picture. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Listing only residues which are non-zero. And then computing the square. 1 squared is 1, of course, 2 squares to 4, 3 to 9, 4 to 16, but reduced modulo 11 becomes 5, 5 squares to 25, and without 22 it has remained 3. And I can keep computing, but what I will get is 3 as the square of 6, which is only knows 36, and without 33 it is 3. 7 squared, 49, without 44 will give me 5. I'll have 9 here, I'll have 4 here, and I'll have 1. So there's a clear pattern in the list of answers. The answers are symmetric with respect to the middle. That's why it's good to take out 0, because it will create a disbalance otherwise. So that is not a surprise, because say 6 is as good as -5, and 7 is -4, and -3 is 8, and -2 is 9, and -1 is 10. So these numbers are mirror images of those numbers with minus sign. And of course squaring doesn't really notice minus sign, so that's why we have answers repeated twice. And these numbers which appear as squares, they're called squares modulo prime or quadratic residues. And only half of our numbers appear as quadratic residues, so the other half are those which do not appear, and they are, well, 2, 6, 7, 8, and 10. So these are not squares modulo 11, also called quadratic non-residues. And again, a clear pattern: there is an equal number of quadratic residues and quadratic non-residues. This is, of course, not a coincidence. This is a general behavior, general pattern. For any prime, the number of quadratic residues modulo a prime is equal to the number of quadratic non-residues. The same prime, and just by knowing that these numbers are equal and the total is prime minus 1, we know that each of them is prime minus 1/2. So the the pattern will persist clearly, that it will be true for any modulus actually, that a number and the negative of that number will square to the same answer. But for primes we can be sure that only 2 numbers will square to the same answer. So the convenient way is to use a little bit of group theory and look at the operation on taking a square as a homomorphism from the multiplicative group to itself. And if I have a prime modulus, then anything but 0 is in this multiplicative group, so I have p minus 1 elements. And then I'm interested in squares, which will become the image of this homomorphism. And by the first homomorphism theorem, I know that I can compute the number of elements in the image by dividing the order of the group, the source, by the kernel, by the order of the kernel. So the order of the group is p minus 1, and the kernel is everything which goes to the identity. The kernel is everything which squares to the identity. Well, congruent mod p, that's what it is, to be equal to the identity in my group. And that, of course, we know is just plus or minus 1, because here we're using the primality of p, because I can rewrite this equation as x squared minus 1 equals 0, or even better, x minus 1 times x plus 1 congruent to 0 mod p. And therefore prime, there are no zero devices, so either this or that is equal to 0, which makes only two possibilities. The kernel is of order 2, and hence the number of elements in the image is half the total. So the other half will be quadratic non-residues. So since this question is a number, a square or not is binary, yeah, obviously yes or no question, it is convenient to encode it, and it was done by Legendre. It is convenient to encode the answer to this question in a function, in a binary function, which is called the Legendre symbol. And the modulus is recorded downstairs, so it looks a bit like a fraction, but it is not. What it is plus or minus 1, depending on a being a square or not. So that is, in other words, 1 on quadratic residues and negative 1 on quadratic non-residues. So one reason for introducing this function is that certain relations between these answers become neat identities. So let's look at the first, which is really saying that we care only about residue of a modulo p, remainder of a modulo p. So if we shift a by copies of p, one or many, the answer to the question if a is a square modulo p will not change. The second property is more interesting. If we take two numbers, modulo p, or just integers, multiply, and then ask this question if this product is a square modulo p, then the answer is hidden in two answers. If we know them, we know that answer, and they are separate questions for a and b. So this is a convenient way of saying four things at once. The first thing is, if we take a quadratic residue and another quadratic residue, multiplying them will give us a quadratic residue. Obvious. The second statement, or maybe it's three really, because multiplication is commutative. Take a quadratic residue and a quadratic non-residue in any order. Multiplying them definitely will give us quadratic non-residue. Again, kind of easy if we have two equations, one is solvable, the other one is not, then multiplying them we will have a non-solvable equation. The last is the most interesting. It is saying that take quadratic non-residue, multiplied with any other quadratic non-residue will always be quadratic residue, will always be square. And that is interesting, and you could argue from contrapositive, of course, but the reverse way in contrapositive will be really division. So in effect, this is a group theoretic argument, so I will not um, will not be able to resist to employ it. And this time we will look, well, what the second equation is saying, that the Legendre symbol is a homomorphism. So we need to see the Legendre symbol as a homomorphism. So if we vary the component upstairs, we'll have a homomorphism into plus or minus 1 into, in group theoretical terms, a cyclic group of order 2. And the kernel, by the definition of the symbol, the kernel is just all squares. So this is my notation for the subgroup of all squares inside the group of invertible integers modulo p. And the fact that this is a homomorphism can be really deduced from one construction in group theory, quotient group construction. All we need to do is to observe that if we take the group of integers modulo p under multiplication and inside it consider the subgroup of squares, we can form a group structure on a set of cosets, the quotient group, and the quotient group will have two elements. There will be only two cosets, squares and non-squares. And as soon as it becomes a group, there is no other option for it but to be isomorphic to the cyclic group of order 2. And so, so we have it. So the Legendre symbol becomes this isomorphism. So that is just the quotient group construction. Just knowing that this is a group will make this happen, the last identity happen. But of course it can be done in a direct elementary way. So let me complete here with last fact about Legendre symbols, about quadratic residues, which is due to Euler. So Euler preceded really Legendre. He discovered that fact, and Legendre is just framed it into language of his symbols. So the Euler's statement is the following, that you can write a formula for the Legendre symbol in residues mod p. You can just take this a and raise it to the power p minus 1/2. P is an odd prime, so p minus 1 is an even number. You can always form this and it will be an integer. Computed mod p, it will be plus or minus 1, and it will just agree with the Legendre symbol. So that is a convenient formula. We will recycle it at least once. And my way of proving it will be by, again, employing group theory. So the group theory here will be just the fact that for prime p's this group is cyclic. It is generated by a single element. The whole collection of elements in here is just the collection of powers of that single element. So that single element is called primitive root modulo p, a, because there are many usually. And in language of group theory, it's just an element with the order, multiplicative order in this case, mod p being just equal to the order of the group, which is p minus 1. So we know that for primes there are always primitive roots. We don't know which integer will be a primitive root, but we know that they are there. Just knowing that they are there will be enough, because any a can be written as a power of our primitive root. And then all we need to know is what happens for the Legendre symbol of such powers. And it's easy to see which of the powers are squares. the powers will have to be even. So odd powers computed, yes, if we treat powers as elements of integers modulo p minus 1, then even powers, well, it doesn't really matter yet, just even powers will be squares, odd powers will be non-squares. So the answer for that Legendre symbol is easy, it's just negative 1 to the power s. But yet let's compute this side of the Euler's claim and see what happens. So we take g to the s, that's what our a is here in the computation, and then raise it to the power p minus 1 halved. So what I can do, I can just rearrange the order in this iterated power computation. Compute first g to the p minus 1 halved power and then raise it to the power s. But g is a generator, so any element will have to be a power of g, and including negative 1, and this element, this power, squares to 1, and it is not 1, so that must be negative 1. So we have negative 1 to the power s. Being a generator, it definitely will give us negative 1 as one of its powers, and that is the power. And so we have it proved. And we'll continue investigating squares and non-squares modulo prime in the next video. So see you soon.